What's up, guys? Back again with another video on structure and bonding. This time we're comparing the strength of ionic bonds. Before we start though, please like, subscribe, share. Let's grow this channel. Let's help as many people as we possibly can. And if you've not checked out my previous video, make sure you check that out because we start looking at charge density there. Let's get into it. So obviously, when we're talking about ionic bonds, we're talking about the electrostatic attraction between oppositely charged ions. There's a previous video looking at that. Now, when we're comparing the strength of ionic bonds, all right, we know they're strong. We know they've got high melting and boiling points because of the strong attraction between oppositely charged ions. But we need a way of being able to compare one set of ionic bonds with another set. And that again comes down to this idea of charge density, right? So charge density, I won't go into too much detail. There we're thinking about ionic radius and we're thinking about charge, right? So the lower the ionic radius, the higher the charge density, right? That's how they sort of link together. So here we've sort of got an illustration of what the ionic radius looks like as we go across. Now, of course, we know group 1 plus 1 charge, group 2 plus 2, group 3 plus 3, group 6 minus 2 because we're gaining 2 electrons, group 7 minus 1. So those are our charges. In terms of atomic radius, they're going down as we move across a period, okay? And I explained in the previous video why that was. As we go down the periodic table here, we've got more electron shells and so a higher atomic radius, or ionic radius is the case here. And we sort of got that summarized here, right? So we can use this to help answer questions that come later on. You can see as we've moved across the period, so we've got lithium and beryllium here. As we've moved across the period, we've got smaller, until we've sort of got bigger with our minus charges as well, because these have gained electrons, right? And as we're moving down the group, we can see our ions are getting bigger. Anyway, so like I spoke about last time, we can sort of have this blanket ends, right? So for metallic bonding, we had stronger attraction between positive ion and delocalized electrons, therefore more energy required to overcome the forces. Let's write our little ends sentence for ionic bonding, right? So here we'll talk about a greater attraction between oppositely charged ions, therefore more energy required to overcome the forces. So particularly when we're talking about melting and boiling points, this is our sort of catch-all when we're comparing ionic bonds, right? So let's do some examples here. So first of all, sodium chloride, magnesium oxide. If we look here, sodium, we've got a 1 plus charge, magnesium 2 plus. Smaller atom here as well, charges is going to be important for, and we've got chloride and oxide. Again, excuse me, chloride here, oxide here. Now, clearly, charges are going to be the most important thing here, all right? Magnesium and chloride, magnesium and oxide, we're going to have a formula of MgO. Remembering our little scales, we've got our 2 pluses from our magnesium, we've got our 2 minuses from our oxygen, that's perfect. For sodium chloride, we've got NaCl. This time we've got our +1 charge from sodium, our minus for chloride. So here it's our charges that really become important. So we've got Mg2 plus and O2 minus versus Na plus and Cl minus. A greater difference in charge. And we've got therefore greater attraction between oppositely charged ions, therefore more energy required to overcome the forces, right? So our answer here is magnesium oxide. Next one, sodium chloride and sodium fluoride. So here we're going to look at the sort of difference maker, right? The sodium's the same, we've got chloride and fluoride. This time we've got the same charges, but as we can see, the fluoride is a smaller ion. Therefore, that 1 minus charge is concentrated over a smaller area. So, worth doing our formulas. We've got NaF, NaCl. So we can say Cl minus and F minus have the same charge. But F minus, a smaller ion, therefore greater attraction between oppositely charged ions, therefore more energy required to overcome the forces. Right? So there are sort of responses to those. Now, here are a few things that I want you to give a go based on that. So a couple of similar questions here, and then a sort of modified past paper question here. Screenshot that, give it a go. I'll answer it at the end of next video. Now on to what we did last time. So here, if you remember, this was sort of like a two-part question. So we had our bit on bromine, which we answered at the end. We said the bromine was a simple structure or molecule, weak forces between the molecules, therefore less energy to overcome the forces. So here now we can say magnesium, a giant structure with strong electrostatic attraction between positive metal ion and delocalized electrons. So that's that first bit, right? So there, why are they different? Yeah, so we've got stronger bonds. So essentially Mg, more energy to overcome forces. And the last bit talks about why is there this greater range between these. And there it's just molten magnesium has stronger bonds. Simple as that. I hope that's helpful. Give the question on the previous stuff a go. Look forward to seeing you next time. Happy revising till then.